I'd like to start part 3 of the Unit 1 lecture, Chapter 21, by doing this example. So in example 21.8, we will be finding the field of an electric dipole at a point C, well, at 3 different points really, A, B, and C, that's shown here on the graph. So as you remember from the previous slides in part 2, the electric dipole is 2 charges of equal magnitude but opposite polarity, and they're spaced some distance apart. So in this case, it's 10 centimeters apart. But we're also going to find the electric field at various points around the dipole by adding the field contributions to the Q1 and Q2 together. We're going to add them, vectorially. So let's get started with this example. And so we kind of have the picture drawn here. I'm gonna draw it again and kind of rewrite what we need to do. So let's start off by drawing our picture again. It's always good to just redraw the picture. It really helps you get into the problem and kind of like see the symmetries and the locations of all the places we're going to be calculating the E field. So I'll use pink to denote my positive charge, blue to denote my negative charge. Okay, there's the dipole. And then green will be the locations where we need to determine the E field due to each charge individually and the 2 charges together. So I believe point C, let me draw a nice straight line here. Point C is going to be directly in the middle between the 2. So that an isosceles triangle is created. It doesn't look too much like an isosceles triangle, but close enough. So here's point C up here. Okay. So what I want to do first is kind of sketch our vectors, because we can always do that right away using the rules for electric field lines coming from positive and negative charges. So let's do that. So I'll use pink for my electric field vector emanating from the positive charge. So actually, before I do that, let's write a quick list of what we need, right? So we need to calculate a few things. So at point A, we need E field due to Q1 at point A. We need the E field due to Q2 at point A. And then we need the total E field at A. Okay? We need to do the same things for point B. Oops. And point C. Okay, that'll help keep things organized. All right, so let's start here. E field at point A due to Q1. So we're going to draw our E field at point A. And since Q1 is positive, okay, the E field due to Q1 should be pointing directly away from Q1. All right, directly away from Q1, because E fields always point away from positive charges. So that's going to be E1A. All right, what about the electric field at point A? Oh, look at that. Sorry, I have my A's and B's switched. Let me go ahead and fix that. Sorry about that. Okay, let's call this B. Or we're going to just go ahead and start with B. All right, so now what about our electric field at point B due to the negative point charge? Well, remember, electric fields always point toward negative point charges. So E2B is going to be pointing to the right. Now my magnitudes, I'm not drawing it to scale, so the magnitudes could be different, right? But the directions are opposite for sure. All right, now let's go to point A. Switch to pink for my positive point charge Q1. So what direction is the E field going to be at point A due to Q1 over here on the left? Well, right, electric field lines, sorry about that, always point away from positive charges. So my electric field due to Q1 should be pointing to the right, away from my positive point charge. Now my electric field line due to Q2, which is negative, is going to point towards negative charges. So I'm going to draw him right on top. Again, not to scale. Okay. And so now C, point C. All right, so remember, the electric field lines point either directly towards or directly away. So what I can do is I can kind of extend that straight line a little bit, okay? So my E field is going to be somewhere on one of these lines. So let's start with Q1. So the electric field at point C due to Q1, which is a positive charge, is going to point directly away. My E field due to the negative charge at location C is going to point directly toward. Okay. So now we have our little cheat sheet. So when we are calculating the magnitudes and assigning directions to the vectors, we're going to be able to just look straight up here at this coordinate system and know if it should be positive or negative, right? Because it's either pointing in the positive X or the positive Y or the negative X or Y. So that's our little cheat sheet. So now we can jump in and start doing some calculations. All right, let's work on point A first. All right, and we're going to be using, of course, the electric field due to a point charge. So let me go ahead and write that over here on the right. Okay, right, where R hat is the direction pointing from source to field, and R is the distance from Q to the point we're measuring, to the field point. What I could say is the source, right? The source to the field point. Okay, so point A, let's calculate electric field due to Q1 at location A. So we're going to have our 1 over 4 pi epsilon naught Q1. All right, so what goes down here? R1A squared R hat. Let's fill in the blanks. That's 9 times 10 to the 9, right? Because this is K. 9 times 10 to the 9. Q1 is 12 nanocoulombs. I don't think I wrote that on here, but oh yeah, it's up there at the top, right? It's 12 nanocoulombs. And that is divided by R1A, the distance between Q1 and point A. So Q1, let's just go ahead and write this down, right? Q1 is right here, Q2 is right here. So we can keep track of it all. So the distance from Q1 to point A is given in the problem as 6 centimeters, okay? 6 centimeters. Convert to SI, square it, okay? The direction is, well, we can probably look at the direction, right? Because we wrote it down here. It's going to be I hat, right? We don't need to do any unit vector conversions because it's all along one axis, okay? It's along one axis. So if you were to use that conversion, you would have a 0 for the y coordinate, and you would get 0.6 divided by 0.6, which is 1. So you're just going, and I'll let you just do that on your own to figure that out and see that, but it's just going to be I hat. Okay, let's get a numerical value for that. That's going to end up being 3 times 10 to the 4 newtons per coulomb I hat. So there's E1A. All right, E2A. That's next. So 1 over 4 pi epsilon naught. Okay. Newtons per coulomb. I always do that. I don't know. I love writing newtons per coulomb. So I'm doing magnitude and direction here, so I am not going to be including any negative signs for Q. Okay, I'm going to let my direction denote my negative sign, and that's just me personally, what I always do. You can do it either way you want, just you got to keep track of them all, right? You got to keep track of that negative. Don't add it in two places, right? Don't add it to your magnitude and the direction, or else it'll cancel out. For me, I'm always going to do positive magnitude and then let the direction decide if there's a negative sign. So what's my R2A? What's my distance from Q2 to point A? It's that little distance right here, okay, which in my picture is 4 centimeters. Okay, and what's the direction of E2A? It's also to the right. It's a positive I hat. Okay, so that's going to give me a numerical value of okay. All right, let's find the total field at A. We're going to add those two numbers together since they're both in the positive I hat direction, right? My resulting vector should be in the positive I hat direction. So and when I add those together, I get 9.8 times 10 to the 4 newtons per coulomb in the I hat. Okay, easy. Okay, let's work on point B now. Electric field due to Q1 at point B. I'm going to get tired of writing 1 over 4 pi epsilon naught, I bet. But we're just going to keep doing it. So that's Q1, R1B squared, R hat. Okay, Q1 is 12. Keep my magnitudes. All right, R1B. Q1 at point B. Distance between Q1 and point B, that's the little distance right here. On my picture is 4 centimeters. Okay, what's the direction? The direction is, okay, 1B, right? It's to the left, away from Q1. So it's to the left, which is negative I hat. Right? My numerical value is then going to be negative 6.8 times 10 to the 4 Newton per Coulomb I hat. Okay, right? I brought the negative sign in the front, right? Because you could do that. It's pointing in the negative I hat direction. E to B. All right, let's go ahead and write the stuff we know off the bat. This is 12. I am dropping my negative. Okay, distance between Q2 and B. Q2 is over here on the right. B is all the way over here. So we have this distance here plus this one, which in my picture is 4 plus 6 plus 4, 14 centimeters, 0.14 meters. What's the direction? Let's go back up. To B. To be or not to be? To be is in the positive I hat direction. Okay. So numerically, we are going to get a small number compared to the other magnitudes, 0.55 times 10 to the 4 newtons per Coulomb, and that is in the positive I hat direction. Okay, let's add these guys together. Oops, B. All right, we're going to have a negative 6.8 times 10 to the 4 newtons per Coulomb plus a 0.55, all in the I hat, which gives me a net negative of 6.2 in the I hat. So it's pointing to the left, okay? Pointing to the left. That makes sense, right? Because we have a really small vector pointing to the right. Why is E2B so small? Why is E2B so small? Because it's really far away, right? Point B is really far away from Q2. So it's going to have a small magnitude, right? Because the magnitude of the E field drops off with inverse R squared. So the result of these two vectors, if I wanted to draw it, you know, a little bit more to scale, this would be a little, that would be a little vector pointing to the right, and the big one pointing to the left would basically eat him. So there we go. Makes sense, right? All right, so far so good. This was pretty easy for parts A and B because the vectors were collinear, right? They're on the same line. Now, when we look at point C, you know, you can kind of see we're going to have to break these vectors up into components, okay? So I'm going to show you, you know, there's two different ways you can do it, right? You can break these vectors up into components the way that we did for example 21.4 with the forces, right? You can use the similar triangles. See the alphas here pointed out in the figure there provided by the book, right? That's cluing you in about some similar triangles where we can break the components into vectors. I'm gonna do it the unit vector way. I wanna continue showing you how to use that unit vector conversion in the case that you don't have a charge at the origin, right? We can only place one charge at the origin here in the dipole. Q2 is not at the origin, so how do we use that, this equation, right? How do we use this if our Q is not at the origin? So I'll show you. All right, so let's do it this way. I'm going to also post a written solution to this that uses the method I referred to in 21.4. Okay, so, but for this one, in the demo, I'm going to show you how to use the unit vector method. All right, so let's get started with point C. Okay, point C. Oops, all right. Let's kind of keep following. E1C, okay? Q1, R1C squared, R hat. All right? 9 times 10 to the 9 newtons meters squared coulombs squared. Q1. Okay, distance between Q1 and C. I believe that was given to us up here as 13 centimeters. Okay, right there. It's 13 centimeters. And our hat, so what is our hat going to be? Our hat is going to be, let's substitute our equation for our hat, right? It's going to be the x coordinate of the point that you want to know the E field, right? Because we're assuming that our point here is at the origin, which it is. Q1 is at the origin, so really there's no assumption necessary, right? Q1 is at the origin, that's the source. The point that we want to know the field, which has an XY coordinate, that's what goes in our formula. So what is that point, right? What is the XY coordinate of point C? Let's look up here and see. Might have to do a little bit of math to figure that out. So we know that this triangle has a hypotenuse of 13 centimeters, 0.13 meters, right? We drop this guy down. We create a right triangle. This bisects the dipolar distance here, right? Which was 10 centimeters. So that means that this side is 5 centimeters, 0.05 meters. And the last thing we need to know in order to get the XY coordinate of C is we need to get this side of the triangle here, right? We can use Pythagorean theorem for that. Upon doing so, you will see that this comes out to be 12. Okay? It's another special triangle, actually. So that one comes out to be 12 centimeters. So now that we've done that simple math, we have our coordinate, right? X is 0.05 meters, Y is 0.12 meters. Okay, so that's our XY coordinate. That's going to go into our R hat conversion. So 0.5 meters I hat, 12.12 meters J hat, divided by what? Divided by what? R, right? The distance between the source and the point, or in terms of the triangle, the hypotenuse of that triangle that gives you your point XY, right? Which is 0.13, right? The hypotenuse that gives you the point XY. So that's how we have converted the R hat to XY coordinates. So let's go ahead and plug in all those numbers here. Okay. In your calculator, you should get 2.46 times 10 to the 3 I hat plus 5.9 times 10 to the 3, newtons per coulomb, J hat. So does that make sense? Okay, pointing to the right and up for E1C, pointing to the right and up. Positive X, positive Y. Exactly right, okay? So we found E1C. Let's find E2C the same way. So we can just go at it blindly, right? We can plug and chug those numbers. That's perfectly fine. The other thing you should work on doing is noticing the symmetry in the problem. Because all these angles are equivalent to the similar triangle down here, we can see that we should get magnitude-wise the same x component and the same y component, but they're going to be pointing in different directions, okay? But let's just go ahead and plug through the math and see. So, E2C and I want to churn through the math anyway to show you how to shift the unit vectors conversion. So let's go ahead and write down the distance between point 2 and C is exactly the same as 1 and C because it's at the point of that isosceles triangle. And so now here we are, we're ready to do r hat. So normally, let's go ahead and write on the side here. Normally, this is how we were converting, right? And this was under the assumption that Q was at the origin. But it's not at the origin. Q2 is not there, right? Q2 is not the origin. Where is Q2? Q2 is at ten centimeters in the x and 0 in the y, right? Those are the coordinates of Q2. 10 centimeters x, 0 y. Where are we? Here we are. So what we need to do is if this conversion was at the origin, right, then we need to shift it, our point Q, as if it was at the origin. And in order to shift it, we would subtract those coordinates, the location of Q2 to put it at the origin. So my x coordinate, I'm going to subtract the coordinate location of Q2. I'm going to subtract, oh wait, well we need to put the location. So y minus 0, right? Because we don't need to shift it up or down. And then the r is going to be the distance between the point and the source, right? Which isn't going to change. It's still going to be 0.13 meters. Okay, so what is our x and y coordinate of Q2? Not of Q2, we already did that. What is our x and y coordinate of the point, right? What are these locations? These are the location of P, right? The place where we're measuring the electric field. So let's go figure out where that is. Well, we kind of did that already, didn't we? It's at point C, which is over 0.5 centimeters or 0.5 meters, and up 0.12 meters, right? That's the coordinate of point C, which is the field point where we want to know the electric field. Same as what we put right here, right? Same values right here. So let's go ahead and plug that in. Oops, I keep wanting to put 0 there. Okay, so what that's going to do is give us a negative I hat direction now, right? 0.05 minus 0.1. No change here. Okay, since Q2 is negative, right, you recall that electric field lines point towards negative charges, so the value that we actually need to use is negative R hat. So if we go ahead and figure out negative R hat, right, it makes switches the signs of our X and Y direction. Okay, so that's what we're going to be plugging in to here, is our negative R hat. Just get rid of that. There we go. So now our X component is going to be positive. It's going to be 2.46. And then our Y will be negative 5.9. Okay, so here is our electric field due to Q2 at point C. And so finally, what we need to do is we need to add those two together to get the total electric field at point C. Okay, so take a look at the X directions, just add together. So we get 2 times 2.46, which ends up being 4.92. What about our Y directions? Equal magnitude, opposite direction, right? So we get a 0. We don't have anything in the Y direction. And we can definitely see that with our vector picture up here. Right, let's kind of illustrate that real quick. So the X component of E1C is going to be right here, okay? And the Y component will be like this. And then the X component of E2C will be right here, right on top. Equal magnitude, actually. And the Y component will be the same magnitude as E1CY, but opposite directions. So you can see that the Y components cancel and the X components add in a very same way as example 21.4, I believe. I think it was 21.4 that we did. Okay, so trickiest part here is just to remember that when you're dealing with a negative charge, right, that your direction of the E field is going to be in negative R hat direction, okay? Which means you need to put your negative sign either here with your directions or remember to include it in your charge. Either way, only one choice though. So that wraps up example 21.8. And we will continue with another example after reviewing a few more slides. So we just did this example. And what we found was that the electric field at point C, due to Q1 and Q2, the X components canceled and the Y components added together. I'm sorry, the y components canceled and the x components added together to form a net electric field in the x direction. So that is just one of the characteristics of a dipole, is that they create a electric field that is anisotropic, meaning it points in one direction. So in that example, right, we added the electric field contributions from each charge together discretely at a location in space. So we can generalize that procedure in the case of a charge that is bigger than a point charge, right? It's an object with a continuous charge distribution. For example, this yellow rod right here, okay, it's a three-dimensional object, and it's made up of charges. And what we do in this case is we take a small piece of that charge. We're going to call it dq, an infinitesimally small piece of charge. And what we do is we can describe, in general, the electric field due to that small piece of charge, and we'll call that dE. All right? And the way we do that is we pretend or assume that this infinitesimally small piece of charge dq behaves as a point charge. And so therefore it follows the equation for electric field of a point charge, which is K, right, 1 over 4 pi epsilon naught charge, dq, divided by distance between the charge and the point that we want to know the electric field, r, and it's squared. And that electric field would be in the r hat direction, right, which is the direction that points from source, dq, to field. So that would be r hat. And so now that we have that assembled here, we can integrate it over all dq, or over all q, right? We're going to integrate dq and turn it into an electric field that has contributions from every single infinitesimally small piece of charge all over the continuous charge distribution. And so there's some procedures that we will be using to turn this into an integrable function, right? Because right now dq is not tied to any coordinate system. It really doesn't mean anything except for an infinitesimally small piece of charge. So we need to kind of turn that into a mathematical function in order to integrate until, right, to start integrating. So let's see how to do that. So the first thing we need to do is we need to address what dq is, okay? So for these charge distributions in this chapter, we are going to be assuming that they are all constant or uniform. So what this title of this slide should say is finding dq for various uniform / constant charge distribution. So what do I mean by uniform or constant? Well, what I mean is that the ratio of charge to length, or charge to area if it's a two-dimensional object, or charge to volume, the ratio is constant. Okay, so these are charge densities right here. Okay, those are all charge densities. And in the case of a line charge, the charge is distributed over one dimension, okay, in a straight line. And so the charge density is just going to be the total charge divided by the length, right? Units of charge per unit length. And so if that's constant, equal to some number, right, which we're going to denote lambda for line charges, if that's constant, that ratio of total charge to total length should be equal to the ratio of infinitesimal piece of charge dq to infinitesimally small length of that charge dx, right? This equality is true if lambda is uniform or constant, a constant number. So taking that into account, we can solve for dq in terms of integrable functions. Okay, in this case, that function is just a constant lambda, right? A numerical value, which is q over total length L, and dx, which is obviously the infinitesimal length along the x direction. Okay, and so if you were doing this in polar coordinates, which we won't be doing, but if in the future you encounter this, you would be translating it into polar coordinates in this way. If you're dealing with a surface area, if you're dealing with a volume, you would translate dq into Cartesian coordinates in this way. Okay, so I think mainly what you guys just focus on line charge in Cartesian coordinates. And there might be, no, actually I didn't assign any homework problems outside of that. So you're totally fine. Let's just worry about that. Worry about this relationship. And so the next thing we're going to do is we're going to do this example, okay, where we have a charged segment, okay, a line. And so therefore it's a one-dimensional charge distribution along the y-axis, and it extends from positive A to negative A. So I have that example copied here. And so we are going to be calculating the electric field at a point P due to a positive charge distributed uniformly along the y-axis. So let's go ahead and sketch our problem. Actually, I think I'm going to make that a little bigger. And so our charge distribution, it exists on the y-axis between positive A, this is the y-axis, and negative A, okay, giving it a total length of 2A, right? So the point P that we want to know the electric field is a distance x from the origin, arbitrary distance x, okay? So we're going to start off by assembling the electric field vector due to an infinitesimally small chunk of charge, which we can place in an arbitrary location. I'm going to place it right here. So that's my little piece of total charge Q, okay, which I'll call dq. And its location, we're going to need this information for later, but right, its location right now is somewhere on the y-axis, right, given by coordinate y. And the length of that charge, dq, is going to be, try to draw it here, a small, infinitesimally small piece of the y-axis called dy. All right, so we'll need that information. So let's figure out what the electric field looks like due to that small piece of charge. So it's a positive charge, and it's going to be pointing directly away from dq at location P. And so therefore the dE vector, right, the infinitesimal contribution to the electric field is going to be following that of a point charge, which is K, sine of the charge, or magnitude of the charge divided by that distance squared. That's the magnitude of that vector. Okay? And so our job now is to, first of all, convert dq. So the first thing we need to do is convert dq to integrable units. using the fact that the charge distribution lambda, which is equal to the total charge over the total length, is a constant / uniform, right? As mentioned right here, uniform, right? So because that charge distribution is constant, the total charge over the total length is going to equal a number, lambda, which is also going to equal the little piece of charge divided by the little piece of length, right? Because the ratio is constant, that ratio being lambda. And so with that, we can solve for dq, and it's going to be in terms of some values, right? Q is known, the length is known, and then dy, which we know how to integrate dy. So now I can substitute that into my expression for dE, right? So the magnitude of that vector right here is k. I substitute my dq, which is big Q over 2a dy, and all of that is over r squared, okay? And so now the second thing we need to do, I'm kind of writing all over the place here. The second thing we need to do, the second step is, in order to turn this into a function we can integrate, we need to kind of figure out how to talk, what r is, right? R is a variable that represents a distance. R does not have really any meaning in the xy coordinate system. So we need to turn R into a distance in the xy coordinate system. Okay, well, we can do that quite easily. So what is R? Where is R on this picture? Remember, R represents the distance between the charge creating the field and the location that we want to know the field. So R is the hypotenuse of this right triangle. And since we know that the distance between, the x component of that distance r is x and the y is y, right? We can easily see that this distance r can be expressed as x squared plus y squared. And that's because of our placement of that charge being on the y-axis. So depending on, your unique arrangement of the charge distribution, like in your homework, I believe in your homework there's going to be one just like this, and then there's another version where the charge is on the x-axis, right? Your r might change, but in this particular case, our r can easily be represented as square root of x squared plus y squared. So let's go ahead and make that substitution now. So our dE, I'm kind of changing colors, is kq over 2a dy divided by square root of x squared plus y squared squared, right? Which just gives me now kq dy over 2a times x squared plus y squared. So now it's starting to look like a function that I can integrate, right? But before I do that, before I integrate, it's actually going to be a lot easier for you to split this magnitude, this vector here, right, into x and y components. So this is where my x component would be. That's where my y component would be, right? It's going to be a lot better for you to do that. So let's go ahead and do that. So that dE magnitude, right, can be split into portions on the x-axis and portions on the y-axis. So it's just like a vector. It's still a vector, right? It just has some differentials in it. But it's still a vector, and we can definitely break it into components. So we're going to do that with the method of similar triangles. So if this is a right triangle, and we can define this guy as theta, and then that means that this can also be theta, right? They're equal angles, so therefore we have two similar triangles. Here's one, here's the other. We can use that to our advantage in order to express DEX and DEY in terms of knowns in the problem, okay? So knowns in the problem, we know this and we know this. I know they're variables, but we know those. We're just expressing it algebraically, but we know those values. What we don't know is what's DX and what DEX is and what DEY is. So let's use our similar triangles. Let's step 3, break our DE vector into X and Y components. Okay. So I'm going to use the method of similar triangles. So basically, both triangles, the ratio of adjacent to hypotenuse should be the same, right? So in triangle number 1, the adjacent side is DEX, right? It's adjacent to theta. The hypotenuse is my DE magnitude. Which I called DE naught. I don't know why. And in my similar triangle, my adjacent side is X, right? And then my hypotenuse is R, also known as X squared plus Y squared square root. So now I solve for DE X, which is just my DE magnitude times the ratio of X over square root of X squared plus Y squared. So it kind of looks like we complicated things more, right? But in fact, it's actually going to be a slightly easier integral. So let's now find the other component, and then we'll work on those integrals. So opposite over hypotenuse, right, is going to be our DEY over DE. Let's just double check that, right? Here's the opposite. There's our angle. And so then that's going to be equal to Y over R, where R is square root of X squared plus Y squared. So now our DEY is going to be magnitude DE Y over square root of X squared plus Y squared. So let's spell out what DEX is and DEY is, okay, right? Because our DE is up here. Right here. So that was KQ over 2A dy over x squared plus y squared, now multiplied by this factor of x over square root of x squared plus y squared, which leaves us with some constants. Technically, x is a constant, right? Because we're not integrating over x, so x is just a value. dy over x squared plus y squared to the 3/2. So that is the function that we're going to integrate. So if we throw an integral on both sides of this, right, that releases the ex. And so now the function that we will be integrating will be dy over x squared plus y squared to the 3/2. And so that's an indefinite integral. We are integrating over a certain region of y. And what is that region? Well, remember, we're integrating over the entire charge. And the entire charge lives on the y-axis between negative a and a. So those are our bounds of integration. So from this point, you can do a couple of different things, right? You could reduce it down to, right, using symmetry, you could throw a 2 in the front. Okay, qx over 2a, and reduce down that definite integral to be between 0 and a. All right, that'll make some little bit of math easier when it's time to do this integral. And so here in physics world, we're not asking you to, reinvent the wheel every time you encounter an integral. So it's perfectly legal and okay to use a table to find the solution to the integral. Okay, so if you look at the back of your book, in the second appendix, you will see a table of integrals, and this one will be there. But the way it's written in slightly different variables. So the table integral in the back, if I remember correctly, it's dx over x squared plus a squared 3/2 equals 1 over a squared. Let's see, 1 over a squared, 1 over square root of x squared plus a squared. I'm going to have to, let me just double check that real quick. Okay, so the integral is actually x over square root of x squared plus a squared. So that's the table integral, and it's in variables. Basically, our integration variable for the table is x, but we need it to be y, and our constant in the table is a, and that is actually for us an x. So when we use this table, we need to make sure that we are correctly translating the table integral to our problem. And you know, there's some common letters here, so it's real easy to get confused. So do it slowly. So when I do that, I can write the result of this integral for ex. And so all my constants stay in front. I'm going to get rid of the 2's. So I have kqx over a. And that is multiplied by the solution to the integral, 1 over, let's make sure we use the right units, right? 1 over x squared y, just double checking, y over square root of y squared plus x squared, evaluated between 0 and a, and evaluated between 0 and a, so I will be plugging in, remember x is just a constant, a over square root of a squared plus x squared minus 0, right? Because I'm plugging in now y equals 0, which is in the numerator, and therefore makes that second term 0. So now if I combine all my terms together, I have a cancellation of x, I have a cancellation of a, and what I end up with is kq over x times 1 over the square root of a squared plus x squared. So that is the x component of the electric field, a distance x away from the origin on the x-axis. Okay, so let's do the same thing now for EY. So let's get our integral assembled. So let's go back up here. Okay, let's express EY in terms of the magnitude of dE times y over square root of x squared plus y squared. So dEy is going to be equal to dE kq dy over 2a times x squared plus y squared times y over square root of x squared plus y squared, right? Because that was our scaling factor. So now when I rearrange this and I move all of my constants to one side, I will end up with y dy over x squared plus y squared to the 3/2. Okay, so now we can integrate both sides. So if I integrate the left, I get ey. If I integrate the right side, push all those constants over, and the integrand ends up being y over x squared plus y squared to the 3/2. Now that is also a table integral. And let's go and see what that integral is. Here's the back of your book. Okay, we're in Appendix B. And so we're looking at that last integral here. All right, because we have the the variable of integration in the numerator x divided by x squared plus a constant squared to the 3/2. Okay, so that equals negative 1 over x squared plus a squared. So in our units, that's going to end up being, so the table integral, so x, let's go ahead and copy it down. That being negative 1 over square root of x squared plus a squared. So our x's turn into y's, our a's turn into x, right? So now we can write down the solution. Oh, and oops, right, the bounds of integration are still from negative a. I didn't do my 2, right? So it's from negative a to a. And then I can do my trick to reduce it down to be 2 times the integral from 0 to a. So I'm just going to leave it this way for now, just to kind of do it both ways, right? I don't need to reduce my limits of integration by half. It's really not that difficult of integral to solve, so I'm just going to leave it for now. You just got to watch those negatives here. So we have kq over 2a, and then the solution to that integral is negative 1 over square root of y squared plus x squared, evaluated from negative a to a. So let's go ahead and do that. So I have negative 1 over square root of a squared plus x squared minus a negative 1 over square root of negative a squared plus x squared. All right, negative a squared becomes a squared. So essentially, I am subtracting the exact same term from the other, right? So this ends up being 0. So there's no y component for the electric field in this symmetric arrangement. So let's go ahead and let's kind of prove that to ourselves, make sure our math was right. So here I chose an arbitrary dq, right? A distance y from the origin. So now what if I choose another dq, a distance negative y from the origin, right? Symmetric. Let's draw the electric field vector there. And we'll kind of prove to ourselves that we do get the y components canceling. So we go ahead and draw our line. Okay. I'm going to erase this guy, get that out of the way. All right, let's look now at our dE vector pointing up. I'm going to I'll go ahead and use green for that, right? So it's pointing away from dq, right? Here's our other little practice dq. It's pointing away from dq because dq is positive. Boom. We're going to have an x component along this. The magnitude will be identical to DEX before, and then we're going to have a y component pointing up, magnitude equal to this DEY component, but the signs will be opposite, right? So the y's, you can see, will be canceling out, and the x's will be adding. So that concludes this example. Okay, I showed you some techniques
on how we as physicists like to tackle these integrals, right? We can just use a table. We're not reinventing the wheel. So we also looked at the 2 steps, pretty much the 3 steps that you need to do in order to tackle any problem like this. So there is a problem in your homework just like this. So make sure you understand how to do this one first and then go on to those homework problems, okay? So this is going to also conclude chapter 21. This is everything I wanted to discuss with chapter 21. The last section, right, that we do, part 3, we're just talking about how to calculate the electric field for multiple particles or continuous charge distributions. All right.